Hello. Hello.
Hello.
Yeah. So we'll continue with infinite series. So right now, first what we'll consider is basically infinite series with all positive terms. With all positive terms. Why? Because if you have an infinite series with positive terms, so it will look something like this. N is equal to 1 to infinity un such that un is greater than equal to 0 for all n belonging to n, then the sequence of partial sums that you will have, the sequence of partial sums, which we defined in the last class, which was S1, S2, and so on, right? Now, these sequence of partial sums will be monotonically increasing. Why do you think it will be monotonically increasing?
सर बिकॉज वो टर्म ऐड होगा और हर बार मतलब वो पॉजिटिव टर्म्स है जो भी ऐड हो रहे हैं.
So these terms are all positive. Therefore, whenever you add, it will all
Hmm.
become increasing, right?
Right.
So why are we considering positive terms? Because this sequence of partial sums is a monotonically increasing sequence now. And previously we have learned that monotonically increasing sequences, you can easily figure out convergence divergence. The only thing you need to check is whether it is bounded or not, right? If it is bounded, then it is going to be converging. If it is not bounded, it will not converge, right?
Right.
This we saw earlier for monotonically increasing sequences. So that gives us a theorem that a necessary and sufficient condition for the series n is equal to 1 infinity un, where un are all greater than equal to 0, to be convergent, is that the sequence Sn of partial sums is bounded from above, is bounded above. That means Sn is always less than basically some number, no matter what n you can get, right? Even if n tends to infinity, Sn should be less than some number, right? Correct.
Right. Correct.
The way you can say this is that u1 plus u2 plus so on plus un will always be less than k for all n. No matter how big n you take, this will always be less than k. If you can prove this, then your sequence is convergent. The only condition here is that the terms are positive. If the terms are positive, then the partial sum sequence is monotonically increasing, and a monotonically increasing bounded sequence is convergent, right?
Right.
So that is one way to check for convergence of these types of infinite series. The second theorem is related to that. It is just an extension of that, which says a series of positive terms is divergent. Sorry. If each term after a fixed stage, is greater than some fixed positive number, is greater than some fixed positive number. So basically what this is saying is that what is happening is if each term after some stage is bigger than some fixed positive number, then obviously the sum Sn when n tends to infinity will never be less than any fixed number. Because you understand why this will be divergent. Like suppose you have some series is like this 1 plus 2 plus 3, or maybe some smaller series. Suppose it is like this 1 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by say 6. Suppose it is like this. Basically what you are saying is each term after this is greater than 1 by 7, right? You are understanding what I'm saying? Each term after this stage is definitely greater than 1 by 7, right? You have to say something whether you understood or not.
Right.
Then why will it be divergent? Why will this series be divergent? Because now you can no longer say that sum to n terms, which is 1 plus 1 by 4 plus 1 by 5 plus 1 by 6 and so on 1 by 6 forever, is always less than some fixed number. Because you can create a number which will exceed that number. Because there are now infinite terms, no, here. Infinite 1 by 6s are there. So you can never get the condition that the sequence of partial sums will be bounded now, because you can always take enough of the terms here, enough terms in n to exceed any k, because we know that the terms are not diminishing, no, they're fixed. At least they will be 1 by 6, right?
Right.
Are you understanding what is happening?
Right.
For the sequence to be convergent, what had to happen? U1 plus U2 plus UN had to be less than some k, right? For any number of n, any n, right? Suppose you had such a k, like suppose we assume that this type of series is convergent. We assume the opposite. Suppose there is a k like that. Now what I can do, I can disprove that by saying that this series is bigger than this series, right?
Right.
And this series, you can find enough terms here that it will exceed k, right? Because I can choose enough 1 by 7s and it will exceed whatever k you pick, right?
Right.
No matter what k you decide, I can choose enough 1 by 7s to make that much happen, right? Make it bigger than this, right?
Right.
So that means that this series itself, the second series here itself, is not following the criteria for convergence, so it is divergent. And that means my series here, which is bigger than this series, will definitely diverge. Are you understanding?
Yes, sir.
Basically, the first thing that you were saying was an infinite series is going to converge if you can say u1 plus u2 plus some un will be less than k for some k. That was the first condition that we said. Now theorem 2 is saying that a series of positive terms is divergent if every term after a fixed stage is greater than some fixed number, some fixed positive number. Here the fixed positive number was, let's say the terms were 1 by 6. So fixed positive number could have been anything less than 1 by 6. And as soon as the terms are greater than that fixed number, now this condition that u1 plus u2 plus un is less than some k can never be true, because you can take enough terms here using these 1 by 6 and all to exceed k, right?
Right.
Okay, so that is important to understand both these theorems. Then we have theorem 3, which says if each term of a series un of positive terms does not exceed the corresponding term of a convergent series Vn, then un should be convergent.
It should be convergent.
So this is obvious. It is saying that if you have a un series of convergent series of un terms, and every term of un series is less than equal to terms of, oh wait, I said the opposite thing. So we don't know anything about un series. We know that vn series is convergent, and terms of un are less than or equal to corresponding terms of vn. So since vn series converges, un will also converge, right?
Right.
And similarly, there is a theorem which says that for if each term of each term is greater than corresponding term of Vn and Vn diverges, then Un diverges. These are obvious statements, right? Are you understanding?
Right.
Then theorem 4 is, if this we have already seen before, but we'll write that again. If this series is a series of positive terms and limit n tends to infinity un is not equal to 0, then what should happen to un series?
Then it should diverge.
It diverges. We saw this in the last class. Then the next one is, if un and vn both converge, then the series with terms un plus minus vn will also converge, right? This makes sense because both are convergent series, so you can manipulate the terms, add or subtract, and you will still be able to find a new series which will converge, right? This is easy to understand, right? You have to say something, bro.
Right.
Are you understanding theorem
Right.
5?
Yes, sir.
If you don't say anything, I will not know whether you got it or not. You have to ask if you don't understand.
Okay, sir.
Next one is if this series converges and this series diverges, then un plus vn will diverge. Here, obviously, the diverging part makes converging means it will be a finite set of terms. It will tend to a finite limit. But the diverging part is means that it is tending to infinity or something. So then it will diverge. The sum. Right? It should be fairly obvious why. Because the terms become larger and larger here. So it will dominate whatever happens to the un. Right?
Right.
So with this in mind, we'll look at some questions. So this is show that the series summation n is equal to 1 to infinity 1 by n to the power 1 by n diverges.
So limit n tends to infinity mu n देखेंगे.
Limit n tends to infinity क्या आ रहा है?
Limit n tends to infinity mu n देखेंगे, वो 1 आ रहा है.
How do you calculate limit n tends to infinity 1 by n power 1 by n?
सर वो tending to 0 to the power tending to 0 का फॉर्म बन जाएगा.
What?
Tending to 0
हाँ, but
to the power tending to 0 का indeterminate फॉर्म बन जाएगा.
so how will you get the answer?
e की मतलब e की पावर में ले जाएंगे. e की पावर लिमिट e to the power limit n tends to infinity ln 1 upon n.
How do you know that? Why?
सर मतलब क्योंकि कोई भी k को हम e to the power ln के लिख सकते हैं ln की प्रॉपर्टी से.
So you're saying this is limit n tends to infinity e power ln 1 by n to the power 1 by n.
राइट.
Now what?
अब इसको मतलब लिमिट को अंदर ले जा सकते हैं e की पावर में. हाँ, अब इसको जो है उससे कर सकते हैं, एल हॉस्पिटल रूल से कर सकते हैं. टेंडिंग टू 0 टू इनटू टेंडिंग टू इंफिनिटी का डिटरमिनेंट फॉर्म बनना है, उसको डिनोमिनेटर में ले जाके फिर एल हॉस्पिटल रूल से कर सकते हैं.
So you are getting what?
वन आंसर आ रहा है
So that means that
वो डाइवर्ज करेगा क्योंकि लिमिट n टेंड्स टू इंफिनिटी म्यू n is not equal to 0, therefore it will diverge.
okay. Then let's say you have the series summation n goes from 1 to infinity r power n. Now, when will this converge or diverge?
Limit at a plus r square plus 1.
Yeah. What are you saying?
सर कुछ नहीं वो अभी कर रहा हूँ सर जब r मतलब जब r -1 से 1 होगा तब मतलब कन्वर्ज कर जाएगा ये।
Right now, we are not considering the case when r is negative. R is only positive here. Because if r is negative, then the series will have positive and negative terms alternating, right?
राइट तो r 0 से 1 जब होगा तब
When r is less than 1, it will converge. Why?
राइट
Why?
भाई बेसिकली जैसे हम इसमें S1 निकालते थे फिर S2 निकालते थे फिर Sn निकालेंगे तो Sn आ जाएगा r प्लस r स्क्वायर सो ऑन एंड ऑन टिल r टू दी पावर n वो जीपी का फॉर्मूला बन जाएगा तो फिर कैलकुलेट करेंगे तो आएगा r इंटू 1 माइनस r टू दी पावर n अपॉन 1 माइनस r टू दी पावर n अपॉन 1 माइनस r ऐसा आ जाएगा तो जब इसे लिमिट n टेंड्स टू इंफिनिटी ले जाएंगे कन्वर्जन और डाइवर्जेंस चेक करने के लिए तो n टेंड्स टू इंफिनिटी ले जाएंगे तो अगर r लेस देन 1 होगा तो कन्वर्ज कर जाएगा वो और ग्रेटर देन 1 होगा तो फिर वो डाइवर्ज करेगा क्योंकि वो और में n
To
की
show
पावर
that it
में
is bounded from above, right? To show that Sn is bounded from above. Converging दिखाने के लिए क्या दिखाना है?
सर वो मोनोटोनिक तो है ही
हाँ,
क्योंकि पॉजिटिव टर्म्स ऐड कर रहे हैं अब हमें बाउंडेड दिखाना पड़ेगा
तो तुम लिमिट क्यों लिखा रहे हो?
सर पिछली क्लास में हमने वो भी तो करा था कि लिमिट n टेंड्स टू इंफिनिटी Sn उससे भी तो कन्वर्जेंस और डाइवर्जेंस करो
लिमिट n टेंड्स टू इंफिनिटी Sn करने से क्या होगा?
सर उससे भी चेक किया था हमने लास्ट क्लास में
हम लिमिट n टेंड्स टू इंफिनिटी Sn करोगे तो क्या होगा उसमें? क्या कंडीशन है वो? क्या कौन सा थियोरम है ये? बताओ मुझे देख के। पिछली क्लास में जो तुम बोल रहे हो
सर
कौन सा थ्योरम? लिमिट n टेंड्स टू इंफिनिटी Sn वाला कौन सा थ्योरम? मुझे तो कोई थ्योरम नहीं याद है Sn का लिमिट लेना।
सर जो हमने सिग्मा 1/n/n+1 था, उसमें तो हमने लिमिट n टेंड्स टू इंफिनिटी ऐसा नहीं करा था।
Sn किया कि un किया?
सर ऐसा नहीं किया था उसमें तो।
कौन सा सीरीज है?
लास्ट क्लास में ही करा था, समेशन 1/n/n+1, उसमें एसएन का ही करा था, वो टर्म्स कैंसिल हो रहे थे, फिर n टेंड्स टू इंफिनिटी लिखे गए थे।
उसमें हम लोग ने Sn का लिमिट ले लिया था।
यस सर।
Sn का लिमिट नहीं लिया जाता है। Sn को यू हैव टू शो दैट इट इज बाउंडेड।
नहीं बट सर शुरू शुरू में लिया था हमने।
शुरू शुरू में लिया था।
हाँ सर, जब शुरू किया था इनफिनाइट सीरीज।
मैंने एक बार भी नहीं तुमको बोला है कि लिमिट ऑफ Sn इज टेंडिंग टू थिंग देन इट इज कन्वर्जेंट।
नहीं, कन्वर्जेंस में डाइवर्जेंस की।
You have to show that Sn is bounded. That is what you have to show. The only thing where you take a limit is limit n tends to infinity un.
ऐसा में नहीं लेते सर।
Sn में you have to show that it is less than something.
फॉर इट टू कन्वर्ज।
If Sn is bounded, then it converges. If it is not bounded, if its limit is infinity, then it diverges. Basically, it means that it is becoming very big. When we are saying limit of n tends to infinity, Sn tends to infinity, then we are saying it is becoming very big. But if it is a finite value, you have to say that it is less than something.
तो बेसिकली हम उससे बाउंडेड प्रूफ कर रहे हैं।
उससे हम लोग बाउंडेड प्रूफ कर रहे हैं. So
तो इसमें लिमिट n टेंड्स टू इंफिनिटी Sn
is tending to what?
1।
So you can say that 1 or higher than 1 can be an upper bound, right?
राइट।
So this will converge only if basically your common ratio is less than 1, right? Correct.
करेक्ट।
If you have a series like this, suppose the series summation 1 by n power lambda. We have to understand when will this converge? When will this converge? So here n goes from 1 to infinity. So the series looks like this: 1 by 1 power lambda plus 1 by 2 power lambda and so on. This is your Sn would be till 1 by n power lambda. We have to figure out when will this series converge. So one special case is Special case is when lambda is equal to 1. In that case, it becomes the harmonic series,
Yes.
which is 1 plus 1 by 2 plus 1 by 3 and so on. And last class we were discussing that there is a way to prove that it is diverging. The way to prove it, have you searched for the way to prove that it is diverging?
No, sir.
क्यों? बोला तो मैंने देखने के लिए.
पर वो भूल गया.
और क्या कर रहे हो मैथ्स के अलावा? भूल कैसे जा रहे हो? और भी कुछ काम है क्या तुमको?
हाँ सर.
क्या काम है?
वो कुछ काम है.
Why are you not doing what I'm telling you to? You have to find out things, no, after class.
Sorry, sir.
One, you can group terms here, 1 plus half. And then you can say 1 by 3 plus 1 by 4, the next two terms. Okay, I'll do it on the next page. Half plus 1 by 3 plus 1 by 4. So on. So you can say first two terms I will group. Then I will group the next two terms. And then the next four terms. And so on. After that, you'll group the next 8 terms. So you can say that this is greater than half. This is greater than 1 by 4 plus 1 by 4 or 2 by 4. Right? This will be greater than 1 by 4 plus 1 by 4, right? Correct?
Correct, sir. Correct.
This will be greater than 1 by 4
Plus
1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8, which is 4 by 8, right?
right.
Then next you will take 1 by 9 onwards, you will take 8 terms till 16, right? And then you will say greater than 1 by 16 plus 1 by 16 plus 1 by 16 8 times. That will also be 8 by 16. So ultimately, what are you proving? You're proving that you can group the terms of this infinite series in such a way that you will get it always greater than 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2, right? First two times you take 2 terms, then you take 4 terms, then you take 8 terms, then you take 16 terms. समझ में आ रहा है? Are you understanding? Here you can take 8 terms.
Right, sir.
Always you can now add up like this and add up like this, and you can say that this series is greater than this, and this is clearly diverging because there are infinite terms here, right?
Right.
So in the general case of 1 by n power lambda summation, if lambda is equal to 1, it diverges. If lambda is equal to 1, series diverges, right?
Right.
There is a way to prove, similar way to prove grouping, saying that if lambda is greater than 1, the series will converge. Series converges. And if lambda is less than 1, series will diverge. If lambda is less than 1, series diverges. So basically, series will converge only in the case when the powers are bigger than 1. In other cases, when it is equal to 1 or powers are less than 1, it will always diverge. The proof for this is also similar. It is by grouping of the terms and find some tricky proof, but we don't need to worry about the proof right now. You just need to know this as a fact because this is a very common series. You need to know that if it is power 1, it will diverge, and if power is lower than 1, it will diverge. And if power is greater than 1, it will converge. Right?
Right.
So that is something that you need to be aware of. Then some limits that you need to be aware of because you might need them. I hope these limits are clear to you. Limit n tends to infinity 1 plus x by n power n. What is the value of this limit?
It's not converted. E to the power x.
And okay, fine. I'm assuming that you know these types of things. There is also one more, which is limit n tends to infinity. Suppose c naught n power p plus c1 n power p minus 1 plus c2 n power p minus 2 and so on. This is a polynomial on top. Cp minus 1 n plus cp divided by, here you have d naught n power q plus d1 n power q minus 1 and so on till dq. If I have to find this limit, what are the possible values that will come here? There are three possibilities.
Yes, sir. 0.
When will it be 0?
अगर Q की डिग्री ज्यादा है P से तो
Q is greater than P. What else?
सर वो the infinity भी जा सकती है, does not exist क्यों?
If P is greater than Q.
P equal to Q तो finite value आ सकती है.
What is the finite value if P is equal to Q? C naught by D naught.
Yes.
Right?
Right.
You will divide by n power P.
Right. P equal to x to the power.
Okay. Now, the reason we discussed these two series, this one and this one, the reason we discussed the convergence and divergence of these two series is because now we will use them for different types of comparison tests. Different types of comparison tests. So we have many tests for convergence. And we will look at some theorems. We talk about how to test for convergence by comparing different series. Like we know right now that this converges if r is less than 1. And this converges if lambda greater than 1. Right?
Right.
Now you will use this information in different convergence tests. So the first one is, let summation un and summation vn be two positive term series, positive term series, such that summation Vn is convergent and there exists M belonging to natural number such that Un is less than equal to Vn for all n greater than equal to m. Okay. Then you can say, then the UN series is convergent. What is this theorem saying? There are two series. We know one of them is convergent, right?
Right.
They are positive term series. One of them is convergent. And we know that after some cutoff point, all the terms of the second series are less than the terms of the convergent series, right?
Right.
After some value m, there is a m like that, after which every term of the UN unknown series is less than the terms of the known convergent series. Then the unknown series is convergent. Okay.
Okay.
Because if there is such an m, there are infinite terms after m, and there are only finite terms before, right? So if infinite terms are lesser than convergent term series, then the finite part doesn't affect convergence divergence, right? Even if we deleted all the terms before m, right? Correct.
It would stay the same.
So we can create a new series un dash by deleting the terms of before m, right? And we will say every term of un dash is less than vn, right?
Right.
So un dash is definitely convergent. And if you have a convergent series un dash, we can add all the finite terms back, and this doesn't change the convergence of un, right? So we have seen that theorem before, that you can add, subtract finite number of terms to any convergent series and it doesn't change its behavior.
Right.
So by that, so you should understand this theorem. It says that after some point, if an unknown series is always lesser than a known convergent series, then the unknown series is convergent, right?
Right.
Now, same theorem, the opposite thing can also be said. Like you have two series, UN, Vn, and Vn is divergent. And you are saying there exists some m belonging to natural number such that Un is greater than Vn for all m greater than, for all n greater than m, right? Then you will say Un is divergent, right? It is just the opposite thing. It is saying that after a point, if all the terms are bigger than a diverging series' terms, then obviously this series is also divergent, right?
Right.
Same theorem for divergence, correct?
Correct.
The next one is this one. Let Un and Vn be two positive term series, such that limit of n tends to infinity Un by Vn is equal to 1 and not equal to 0, is equal to not 1 L, which is not equal to 0, Okay. Then the two series have identical behavior with respect to convergence. Basically, it means that both will be converging or both will be diverging in relation to convergence. And second, if L is equal to 0 and Vn is convergent, Vn is convergent, then Un is convergent. You understand what is this saying? What is this theorem saying? It is saying find out the limit n tends to infinity of Un nth term and Vn, right? If the limit is finite and non-zero, then the two series have identical behavior. So either both will converge or none of them will converge or both will diverge, right? Are you understanding what I'm saying?
Right.
If L is 0, you will say that if the denominator is convergent, Vn is convergent, the numerator will also be convergent. L is 0 basically means that Un is small compared to Vn, right?
Right.
When will this limit tend to 0? When Un is much smaller
Right.
than Vn, right?
Right. Right.
If the Vn part was convergent, then Un part is convergent because it is smaller than the Vn. If it's a finite non-zero limit, then obviously both will converge or both will diverge. Now, the way you use these results is by comparing it with some known series. Like you'll be given a series and you'll compare it with some known series whom you know is already convergent or divergent, right?
Right.
And what kind of series you can use? You can use series like this, you can use series like this, or specific values of r and lambda, right?
Right.
Because you know their convergence, divergence, so you can use any of them as Vn,
Right.
right? Write down these questions. These are the questions that we'll discuss next in the next class. You have to basically figure out the convergence, divergence of these series. these 8 questions we have to discuss. You can try these. We'll discuss it in the next class. Test for convergence or divergence. Using whatever we have learned so far. Have you written all of them?
Yes, sir.
Okay, so try these later and we'll discuss them and more questions in the next.
Okay.
Okay, that's all now.